Okay, hello everyone. So before we get started on the details of this titration experiment, I want to go over solutions, what solutions are, and some definitions of solutions. You may have already had this in lecture, but it wouldn't hurt to do some review. A solution, just going to write that here, solution. It is a mixture of at least two pure substances. That is the general definition of a solution. Now, we typically think of solutions being liquids, but they don't have to be. A solution could be air, and a solution can even be a solid. So it's a mixture of at least two pure substances. They can be 3 or 4 or 5. All right, major component of this mixture. The major component is known as the solvent. Solvent. Okay. So in the experiments that we're going to be dealing with in this, the titration of acetic acid, the solvent will be water. The minor components. Minor components, sometimes there's more than one. Those are called solutes. Okay? Solute. Okay. So now with this set up, I want to talk to you something about concentration of a solution. How much solute is in a given volume of the solution? Okay? Now, a lot of students confuse solution and solvent together, right? They're different. The solvent and solute together make up the solution. But there are all kinds of concentration terms of the amount of solute in a given volume of solution. One that is probably used most prominently in chemistry is something called molarity. It's a concentration term, molarity. And it's often represented as a capital M. And the units for molarity are moles of solute for every 1 liter of solution. So that's the unit for molarity. Written in a more abbreviated form that way. Moles per liter. Moles per liter. Okay. And we're going to be dealing with this concentration term in this experiment. All right, so let's talk about the experiment. So the reactions we'll be doing in this experiment, 2 reactions, but both of them are an acid-base reaction. And I've written the acid-base reaction up here. HA is just a generic term for the acid. Okay, there can be 2 acids. One acid will be something known as potassium hydrogen phthalate. We abbreviate that as KHP. And there's nice information in department handout on KHP. The second acid we're going to be dealing with in this experiment is acetic acid. Acetic acid. Right? So solutions of acetic acid are known as vinegar. Right. So this is the general reaction right here, and this chemical equation is balanced. Right. So in both cases, 1 mole of the acid will react with 1 mole of sodium hydroxide to produce 1 mole of the sodium salt, right, the conjugate base of this acid, sodium salt, and 1 mole of H2O. Right, that's the ratio. The ratio is 1 to 1 to 1 to 1. Doesn't have to be 1 mole. If we had 0.1 moles of the acid, then it would take 0.1 moles of sodium hydroxide to react with it to make 0.1 moles of the sodium salt and 0.1 moles of water. A real-life reaction would be hydrochloric acid solution plus sodium hydroxide solution to make sodium chloride, aqueous, plus water. Again, this is a specific reaction. This is the general reaction that's going to cover both of the reactions that we do today. And HA is just written in generic form. HA is represented by here. The A part would be the chloride. And this H, of course, is the hydrogen. Okay, so this is the overall reaction. And the point being, it is 1 to 1 to 1 to 1. The stoichiometry is. Okay, so titration. Suppose we have a solution of sodium hydroxide, right here, but we don't know its concentration. We're unaware of its concentration. But we can take KHP, potassium hydrogen phthalate, we can weigh that out, determine the number of moles of potassium hydrogen phthalate, and then add sodium hydroxide carefully to this potassium hydrogen phthalate mixture until all of the HA, all of the acid, is reacted. Right? And so since this is 1 to 1, if we know the number of moles of acid we started with, we know the number of moles of sodium hydroxide it took to react with all the acid. Right? The point where this occurs is called the endpoint. The endpoint. Right, so we have an indicator in this reaction mixture over here. And the indicator is phenolphthalein, and it's colorless in an acidic environment. So we make this potassium hydrogen phthalate solution. We know the number of moles that are in there. We add some phenolphthalein to it. Phenolphthalein is colorless. And we keep adding sodium hydroxide until the thing turns pink. Right? So once all the acid is consumed, the solution will turn pink. And that tells us to stop. That's called the endpoint. So in this case, we're adding sodium hydroxide to this analyte over here. This is known as the titrant. This is the analyte, even though we're trying to determine what the concentration of sodium hydroxide is. Okay, at the endpoint, again, we know the number of moles of sodium hydroxide added at the endpoint is the same as the number of moles of potassium hydrogen phthalate we started with. Right? So, do a quick calculation. Suppose we know that we started with 0.00146 moles of KHP. That's what we started with. We weighed out KHP, we took the mass of KHP and divided by its molar mass, and we determined that's how many moles of KHP we're starting with. So at the end point, again, this also has to equal the number of moles of sodium hydroxide. Again, this is at the end point, when our solution turns pink. At the end point. At the end point is when this is true. All right, suppose it took 14.72 milliliters of sodium hydroxide solution to get to the end point. Okay. That's how many moles of KHP we're starting with. And it took 14.72 milliliters of sodium hydroxide to add that many moles of sodium hydroxide. So the question is, what is the concentration of sodium hydroxide? What is the concentration of sodium hydroxide that was in this solution of 14.72 milliliters? That's what we have to determine. Well, Let's think back. Concentration of sodium hydroxide, the molarity, is moles of solute, moles of sodium hydroxide per liter of solution of sodium hydroxide. We have all the information right here. The molarity of sodium hydroxide in this case will be the number of moles of sodium hydroxide present at the endpoint divided by the liters of solution that contained basically this number of moles of sodium hydroxide. There it is right there. Now it's in milliliters, so you have to make a conversion into liters because molarity is always in moles per liter. There. 14.72 milliliters is 0.01472 liters. And so you just do the calculation, and that gives you the concentration of your sodium hydroxide. So I'll do that, 0.001469 divided by 0.01472. All right, so 0.09980 molar. Right? A lot of times we call molarity molar. But again, this is moles per liter. So this is the concentration of the sodium hydroxide that we added to reach the end point, that we added to reach the equivalent amount of moles of KHP originally present. Now that is what this calculation, this experiment is what we're going to do first. This is actually standardization, right? What we're really trying to do is we're trying to use this sodium hydroxide solution to determine an unknown concentration of acetic acid solution. But we have to know what the concentration of sodium hydroxide is to 4 significant figures first. Okay, so a little question I have. Why can't we just weigh out the mass of sodium hydroxide and then dissolve it into 1 liter and get the concentration that way? The problem is that sodium hydroxide is something called the pellets, solid sodium hydroxide, something we call hygroscopic. It absorbs moisture from the air. It also reacts with CO2 that's in the air. So the mass of sodium hydroxide that you're weighing out to make your solution is not entirely sodium hydroxide. Right? Some of it will be water, and some of it will actually be sodium carbonate. And so what you think is all sodium hydroxide, if you were to attempt to make a solution of this concentration, what you think is all sodium hydroxide in the mass is not, in fact. And so your calculation, your preparation of the solution would be wrong. You would calculate this as being the correct concentration perhaps, but actually it'd be a little bit less than this concentration, right? Because the mass you weighed, not all of it is sodium hydroxide. Anyway, this is one of the reasons why sodium hydroxide solutions have to be standardized. And this first step is a standardization of sodium hydroxide. Now, once we've done this, this is a standardized concentration of sodium hydroxide that we can then use to find out the concentration of acetic acid. Okay. So let's look at that experiment. So the same reaction up here applies for the acetic acid solution. So this is the acetic acid now, not KHP. This is acetic acid. It's going to react 1-to-1 with the sodium hydroxide to produce sodium acetate and water. All 1-to-1 to 1-to-1. That's the stoichiometry. Okay. Now suppose suppose 4.72 milliliters of acetic acid solution is titrated with this concentration of sodium hydroxide. We know that concentration now because we did that experiment first. So we have an acetic acid solution now, and we titrated with this concentration of sodium hydroxide to reach endpoint. Question: what is the concentration of acetic acid? Right. What is the concentration of acetic acid in this solution? That's what we have to do. And again, the same principle applies. At the endpoint, the moles of sodium hydroxide we added equals the moles of acetic acid that were originally present in this solution up here. Okay. So let's calculate the moles of sodium hydroxide we added. Well, there are 0.09980 moles of sodium hydroxide for every 1 liter of solution. Okay. And we used, how much did we use? I haven't given you that information yet. I don't know. Let's say that we used 13.05 milliliters. All right. We used 13.05 milliliters of this solution to react completely with the acetic acid that was in this solution. If there are that many moles of sodium hydroxide for every liter, then in this many liters, there is all right, there it is. 0.001302 moles of sodium hydroxide. 0.001302 moles of sodium hydroxide were contained in this 13.5 milliliters, 13.05 milliliters. Okay. That's how much we had to get to the endpoint. And again, at the endpoint, the moles of sodium hydroxide equals the moles of acetic acid that was originally present. So that means there are also 13.02 moles of acetic acid. In this volume up here. So the concentration of acetic acid will equal 0.001302 moles of acetic acid. And it was contained in this volume, right? We want to know the acetic acid concentration of this solution, and there are 4.72 milliliters in that solution. So you do that calculation. Zero 0.276 molar. All right. So now we've determined our concentration of our acetic acid. And this is what you're doing today. This is what you're doing in the experiment. I've already done the experiment. I have the videos ready for you. And we're going to talk about some details on that coming up next. But before I go into it, I want you to understand these calculations as I've done them here. Okay? It's important that you understand what I'm doing here. There is an equation that you can use. And using the equation, in essence, is the same thing that we've done here. But since students like simple equations to plug and play, it often gets them into problems, I'll tell you that. I'm going to go ahead and give you the equation, right? But you better know how to use it. You better know how to use this equation, and you better understand it. Don't just treat it as a black box that you can just plug numbers into and do some simple algebra and get the right answer. Because I can ask the questions in such a way that if you really don't understand what's going on, you will put the wrong values in the wrong spot in the equation. All right? This is fair warning to you right now. And I will ask questions in such a way where if you don't understand what's going on in that equation, you're going to make a mistake. Right? Don't treat this equation as a black box, is what I'm telling you. And here's the equation. The concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. All right? Often you see this as M1V1 equals M2V2. And in essence, this equation right here is the same thing that we did right here. Same thing. This is a more detailed conceptual, right, representation of the problem that you're doing. Breaks it down into multiple steps. This is a condensed version of those calculations over here. This is just condensed. So if you know, let's say the second part of the problem here. If you know the concentration of the base, and you know the volume of the base, and you know the volume of the acid, then you can calculate the concentration of the acid. And if you look at this problem over here, I gave you the volume of the acid. All right, so we have VA. I gave you the concentration of the base right here, so we know M sub B. And I gave you the volume of the base, 13.05. So you can put all those values into this equation and calculate the concentration of the acid. And the reverse is also true. If you're trying to find the concentration of the base, all you need is the concentration of the acid, the volume of the acid, and the volume of the base. Right? And in these titration problems, in essence, one of these will be unknown, and the others will be given to you. The other three values will be given to you. But I'm warning you, don't treat this as some black box that you don't really know what's going on. You just plug numbers in, do the algebra, and it gives you the right answer. Right? Because it's not going to be that straightforward on the quiz or the practical. Understand what I'm doing over here. All right. So, details of the experiment. Titration. What you're going to have is a burette. Burette is a long, skinny glass tube, like so. And down here at the bottom, you have a spigot. And you have a little knob right here. And there are graduations on the burette. Again, this is called a burette. So let's say the meniscus is right here, and in this experiment, the burette will be filled with the sodium hydroxide solution, right? In both cases. So up here is the initial volume. So you read the initial volume on the burette, and you have to read it to the correct precision. I'm not going to tell you. I'm just going to show you the graduations and where the meniscus is in the experiment. It's up to you to determine the correct precision. So you take the initial volume. All right. After you get the initial volume, you have an Erlenmeyer flask down here that contains your sample. All right. So in the first part of the experiment, this flask will contain the potassium hydrogen phthalate, KHP. In the second part of the experiment, it will contain the acetic acid. All right, the point is, you turn this little valve here, and sodium hydroxide that's in this burette is released into this flask. You also have phenolphthalein indicator down here. So sodium hydroxide solution is added to the flask. You swirl the flask around slowly. Well, maybe not so slowly, but you swirl it around to make sure proper mixing is occurring as the sodium hydroxide is added. And then you look very closely and you wait for a color change. Now remember, at the end point, that's what we're looking at. The color change tells you where the end point is. So ideally, you want a very light pink color down here. The lighter, the better. And when I was doing the acetic acid titration, you're going to notice it looked like I was right on the end point, about as good as you can get it. I wasn't quite sure. I was looking at the color. It still, I thought I could see some pink, but I'm not too sure it would be obvious to you through the camera. So I added one more drop, and then boom, the whole thing just turned a really dark pink. That's the problem with these types of titrations. One drop and you can go too far. But the principle would be the same. So we add sodium hydroxide through here, and we wait to get to the end point. And then we stop. We stop. It tells us when to stop. So let's say that after we added sodium hydroxide to get to the end point, the meniscus now is down here. Okay. So this is the initial volume. This is the final volume. Final volume. Okay. So this distance here is the amount of volume that you added. The volume of sodium hydroxide you added to get to the end point. So volume, I'm going to call this IV. This is going to be FV, right? Initial volume IV, final volume FV. So volume of NaOH added equals final volume minus initial volume. Okay. Final volume minus initial volume, and that will tell you the volume of sodium hydroxide solution you added to get to the end point on both the experiments. Okay, that's it. That's all I have. Next up, experiment.